Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 31. So, already we have derived this equation. This was the equation of motion, or the position vector, how the position vector of the third particle it changes with respect to the first particle. So, equation of motion of the third particle with respect to the first particle. And in one shot we have not written this. First we have written the equation of motion for the particle 1, then for particle 3, and then subtracted to get this equation, and nowhere we have violated equation of motion which is described in inertial frame using Newton's second law, and this we will always keep care of. Now, we need to generalize it. Equation for n number of n particles. Or simply we can write this as n particle system. For that, what we do that we write here, we replace 3 by L. by L, that is the satellite, or you can even use the S notation to indicate this is satellite. I have chosen just L. So, replace 3 by L. So, satellite is indicated by subscript L. Therefore, this equation we will write it as a equation A can be then written as R 1 L R 1 L double dot this equal to minus G. Here we have missed out this term R 1 3 G m 1 plus m 2 m 3 divided by R 1 3 whole cube. This we are replacing 3 we are replacing by L, and therefore, we replace this by L here, and this 3 also we need to replace by L. And then again we rewrite for okay. So, here in this case we have just replaced the satellite by the subscript L everywhere. So, 3 is replaced by L in all the places. Now, in the next step we replace 2 by J. So, next step we replace particle 2 by subscript J, and if we do that we will have R 1 L R 1 L double dot, this will be equal to M 1 M 1 plus M L with minus sign and R 1 L whole cube, R 1 L whole cube G times M 2. So, M 2 will replace by J and then R 3 2. So, R 3 2 was replaced by 3 was replaced by L. So, here in this this place, so 2 we are going to replace by J. This is 1 2 1 2. So, this will become R 1 J R 1 J. So, now here it appears like this. You have the M L, this is M 1 and here this is M J. Now, suppose I have to replace, suppose I replace this 1 by I. If we do that, so this will be I L double dot. I am taking time in doing this because I am going step by step. R I L whole cube G M J R L J So, we have converted this all the equation previously we have written in a generalized notation. Now, assuming that we have total n number of particles, then the motion of LTH particle about the ITH particle can be written as R I L double dot. Now, the perturbation term will be more. Perturbation terms we have to increase. R I L whole cube R I L plus, here the summation follows now. So, G M J R L J by whole cube minus and summation from where to where, that we have to take care of. So, here in this case the summation is extending over this j. Therefore, summation will move from j to n. And we will write here j equal to 1 to n, but out of this the out of 1 to say L, and before this the I comes, and then lastly the n comes. So, out of this I and L will not be counted here in this place, in this summation which is indicated here into this with this summation sign. So, this implies that we have to write here j is not equal to L and also j is not equal to I. So, these are the terms we need to put here, j not equal to I, because the ITS particle already is involved here. So, now here also we have to change, we have not changed here in this place. So, this is your M I, we have changed here, but here this was missing. So, we need to change here. One we have done this, this is also M I. So, already the ITS particle is involved here and LTS particle this is involved here, and here whatever is coming, this is because of the JTS particle. So, JTS particle I need to remove this j equal to L and j equal to y and sum it over, and therefore, this j varies from 1 to n, but out of that we have to remove the case j equal to L and j equal to I, and this is your equation which gives you a generalized form of equation of motion of the LTS particle with respect to the ITS particle. That means, it may be your satellite, it can be moon with respect to earth, or in general if you go about any planet, say about the Saturn, or you have the Jupiter. So, Jupiter have its own satellites. So, in that case accordingly you can describe this equation remains valid throughout, provided we choose the frame we need to choose properly. So, in this case for the solar system our frame remains the barycentric frame or barycentric inertial frame. If you are going to this will serve you as the inertial frame. Beside this, you can have your inertial frame located at the Jupiter. So, if you are looking for how the with respect to the Jupiter its a satellite is moving. So, in that case you have to locate the inertial frame at the Jupiter, and Jupiter is moving around the sun. So, obviously, this is not an inertial frame, because it is accelerating toward the Jupiter is accelerating toward the sun, and therefore, it cannot be an inertial frame, but this frame does not rotate along with the Jupiter, it is just translating. Translating means already I have described, its orientation will always remain the same as I am showing here. However, correction can be given, and these are advanced topics which you can find in book by Siedelman. So, it is called the explanatory supplements by Siedelman. So, you can refer to that book if you have access to that book. Okay, so every time we need to take into account one inertial frame, and depending on the situation we have to locate it. If required, proper correction has to be given, and all those things what are required for modeling these things, these are given in that explanatory supplement by Siedelman. Siedelman, exactly I cannot remember his all the alphabets in his name. So, I will leave it, but it is a by explanatory supplement by Siedelman. So, you can look into that. It starts with S I D E something like that, Siedelman. In some of the libraries, this book may be available. Now, we have got this. So, this is our main term, and this is the perturbative term as I have stated earlier, and here in this case. Now, one more point I would like to say here. See, this perturbative term here we are taking only due to gravity. So, this is only due to gravity, but in the case where non-gravitational forces are present, just in the case of say Earth is here, this is your Earth, and around this satellite is moving in the orbit. It is going here in the orbit, and if it is in the low Earth orbit, low Earth orbit. So, at that time the atmospheric drag will also act on this. Atmospheric drag, this will also act on this, and this one we cannot represent using the potential function, while this term we can indicate using potential function, and therefore, if we write in terms of potential function, it becomes little easy to handle. Then we will have the solar radiation term, as I have mentioned you earlier, solar radiation. Then Earth is not a perfect sphere. Okay. If it is a perfect sphere, then there is no problem, but if it is not a perfect sphere, and satellite is also of not, you cannot treat the satellite as a point. Okay. If you have a little larger satellite, so then the situation becomes different. Okay. So, Earth is oblate, that means we will have the extra mass present here, it is a non-uniform. So, because of that our equation here, what we are writing here in this place, this gets, we have to write it in a proper way. Okay. This is just for a particle mass system it is written, but if you have not particle mass system, then the situation is different. If Earth is a particle, satellite is a particle, you are treating like this is okay, but Earth is a finite mass and that too oblate, the situation becomes different. Okay. So, all those things they can appear as the perturbative term, okay, and we need to model them properly. So, we will take these terms as much as possible as we advance. Okay. So, now we will look into the barycentric formula. Barycentric formula. So, here I am not going to derive the whole equation, I will show you that either you write in an inertial frame as I have done earlier, or with respect to the barycentric frame, both are same. This is x, y, z, and we have number of particles here. Okay, and let us say the barycenter is located here in this point. This is your barycenter. Mi and Mj we show here on this point for clarity. This is Rj, this is Ri, Rij, and this is the barycenter is lying here. So, barycenter to the barycenter we have this, let us say this point is B. So, we can indicate this as R O B. This is the point O. Okay. And about the barycenter you have the reference frame located. These are the three axes of the barycenter. XB, YB and ZB. We can connect these points RBI. On this side we can show this as RBJ. So, what we can notice from this place that Rij, this is Rj minus Ri, and already we know that the center of mass of this mutually, this is very visible from the basic principle that the system of particles which is moving under its mutual gravitational act, a system of particles or the particles which are moving under mutual gravitational acceleration, okay, and free from external force like the drag or any other thing, solar radiation or any other magnetic force from the external sides. Okay. So, those things are absent, only the gravitational force is present, the mutual gravitational attraction. So, the system of particle which is free from the external force must, its center of mass must move with constant velocity, and I will show it, definitely I will do that. For two particles already we have done this, and along the same line it can be done for the three particle system. Okay. So, barycenter is a point which is the center of mass of the system, and it moves with constant velocity, and depending on the initial condition it may be either at rest or moving with constant velocity. These are the two situations. So, here R j minus R I, R I j we have written, and this can also be written as R B j minus R B I. Which is obvious from the this figure, and you can check also, this can be checked here, like R B j minus R B I, this equal to R B j is nothing but R j R j minus R B, or from here to this O will remove from this place, this is simply R B. And then minus R I, this vector, how this vector will be expressed? This will be expressed by R I minus R B. So, R I minus R B, R j minus R I, which is true on the left hand side we have written. So, this is the basic fact that once we are looking for motion of one particle with respect to other. So, it does not matter which inertial reference frame we are choosing. The motion equation of motion should be described in inertial frame, but it is independent of the reference frame chosen, and this will be visible from this point. Okay. If you are interested in writing like this, so the equation of motion for the JTS particle about the ITS particle. So, vector going from this is the JTS particle, this is the ITS particle, and this is your Rij. So, this will depend just on the either you write it here in terms of this or either here in terms of this, both are equivalent as shown here in this place. Okay. And therefore, the way we tend to describe the motion of one particle with respect to other, it is independent of the reference frame, and we will complete this. Okay. So, this point is very much visible, and we do not need to elaborate any further on this. So, now let us look into this issue here RBI, which is the point here. So, motion of the ITH particle, we are looking for RBI double dot. So, what this quantity will be? Ri minus Rb double dot. And as I will be showing you that Rb double dot, this quantity is going to be 0. So, therefore, this gets reduced to Ri double dot. So, this is the fact here, that the motion of the ITH particle with respect to the barycenter, which is B, okay, it is shown here. Okay, with respect to the barycenter, it will be the same as the motion of the ITH particle with respect to the x, y, g reference frame, and this fact can be used to simplify your problem wherever it is required. So, with this we can conclude that this tells. Okay, here before writing I would like to state few more things. If you look into the books, okay, many of the books they describe the equation of motion in terms of barycenter, but it is not necessary. You write in any frame, okay, and thereafter you do the subtraction to get the motion of one particle with respect to other. You get the same result, it is not different, okay, because the barycenter is also an inertial frame and you are choosing another reference inertial frame. Individually you are writing the equation of all the particles. So, Newton's law is perfectly applied in that case, there is no change in no error done in that, and thereafter once we subtract the equation for different particles by dividing by the corresponding mass. So, we get the relative motion equation. So, it is so easy to work with, and therefore, do not get this confused if somewhere it is written with respect to the barycenter, or I am using here this x, y and z frame, and in most of the places I have used this kind of notation that this is my frame, these are the particles, I have written equation of motion for this particle and then for this particle, and then subtracted to get the equation of motion of one with respect to other. So, there is no problem in that, and again I have repeated that this is valid, okay, or either you do with respect to the barycenter, that is also valid. This one is much more easier to comprehend, much more easier to write. Okay. barycenter, it may be little complicated from places to places, but it may be required at some time that you need to express your equation of motion with respect to the barycenter. So, in the case of the Sun Earth system, what exactly the thing is happening, your center of mass is located inside the Sun itself somewhere. This is your barycenter here in this place, okay. And then the Sun will be moving about this barycenter. This is the barycenter, and center of mass of the Sun is located as shown by this blue dot here. So, this is barycenter and this is center of mass of Sun, and here this is your Earth. So, center of mass of the Sun will be moving about the barycenter like this, and about this barycenter Earth will also move like this. So, this is the mutual motion, but if you are looking for so in that case what you get, you have the about the barycenter, you can describe the motion of the Sun and you can describe also the motion of the Earth, but most of the time we are interested in finding with respect to the Earth how my satellite will look like, or with respect to the Sun how the motion will appear. If you look into the as we look at the Sun from Earth, so how its motion appears. So, again it is a from that we call the geocentric point of view. By sitting on the Earth, we are looking at the motion of the Sun. So, because if diurnal motion means the daily motion, it is rotating on its axis, because of that you see that Sun is rising, it is going in the sky, and then it is a setting, it is a rising in the east and then setting in the west, and depending on your this latitude, it will appear either overhead at some times or it may be inclined. Many situations they appear. So, geocentric point of view, that how the Sun will appear to move about the Earth. So, this can be one view. Okay. Similarly, the other planets, but other planets what happens that if I have the Sun here and say the Earth is here shown by E, and somewhere the Mars is here. So, these are the orbits. Now, looking at the from the Earth, how the Mars will appear to move, this can be another question. Then inside we have the Mercury and Venus. So, how the Mercury and Venus will appear to move. So, you will see that as the Sun is moving, appears to move about the Earth as we see from the Earth, then the Venus, it remains confined to this range. Venus remains confined to this range, Mercury remains confined to this range. Okay. So, around perhaps 40 degree as seen from the Earth, this angle is confined to some 40 degree. It is not 40 degree on the each side. I do not remember exactly, but it is always this will be visible. Other planets may not be visible at some time, but the Mercury and Venus, they are always visible from the Sun, from the Earth, because they are moving about the Sun, and their deviation will not be more than 40 degree, if I remember correctly. Okay, so, in that case, that also it is a described in the book by what we in the book called the Surya Siddhanta. Surya Siddhanta, this is a book which deals with the planetary motion. So, this describes the motion of the planet with respect to the Earth. So, it is a little complicated and only the geometry is used to solve the problem, because earlier the computers were not used. So, using just the geometry, this motion were described. Okay. and therefore, you might have heard the retrograde motion of certain planets. So, it is basically while you are looking from the earth. So, how the other planets they appear to move, it is going like this. Suppose some planet is going like this. So, this is called the they call it the direct motion, and after some time from the earth it will appear to move in the backward direction, and then again it will become in the forward direction. So, this is because just we are looking from the earth, sitting on the earth, we are looking at different planets. So, because of this our position, this kind of motion appears. So, this is called the direct motion, and this motion, this is called the retrograde motion. Okay. And you can look on the web page. If you search for this, the retrograde motion of the planets as seen from the earth. So, you will get the figure exactly, because I cannot make that much good figure here in this place, and using the graphics you can have a look of all those figures. So, it is interesting that the same thing what we are doing today, this was done much earlier in time, but in a different way, and obviously at that time there is certain difference in the distances, but not much, but the precision in the angle, it is a very good. Okay. Because it was based on geometry. So, the angles were maintained, and distance was not of much importance in this case. People were interested in knowing the position of the various planets and the sun from time to time. So, we close this chapter here, and then we will move to the next lecture. Okay, thank you very much.